With that, ladies and gentlemen, we are now going to move on to our keynote speech. Joining us today will be Professor Chua Seng. He is the KITHCT Chair Professor at the School of Computing, National University of Singapore. He's also the Distinguished Visiting Professor of Tsinghua. Dr. Chua was the founding dean of the school from 1998 to 2000. He's also the director of a joint research center between NUS and Tsinghua to research into big, unstructured, multi-source, multimodal data analysis. His research focuses on the extraction, retrieval, and question answering of text, video, and live media arising from the web and social networks. Ladies and gentlemen, he's the recipient of ACM SIGMM Technical Achievements Award 2015. He's the chair of the steering committee of ICMR and Multimedia Modeling Conference Series. Dr. Chua is the co-founder of two technology startup companies based on research in Next. So for a session towards relation inference and causal reasoning in video, I present to all of you our keynote speaker, Professor Chua Seng. Over to you, sir.
Okay, yeah, thank you very much. Yeah, let me share my video. And okay, I hope y'all can see my screen. Yeah. Thank you for the kind introduction. Yeah, I think you kind of say a lot that. So I guess I will just go ahead straight to the presentation itself. Yeah. So first of all, I'd like to thank the organizer also for inviting me, and I guess as often if we kind of give talks over the internet, especially Zoom and things like that, I do not have any feedback, right? So if there's anything that's unclear, say the loss of voice or anything, please kindly remind me. Otherwise, I would just assume that everything is okay and proceed with the talk. Yeah. So today I kind of will talk about a topic that is kind of deep inside my interest, which is kind of visual analytics, in particular on relation inference and causal reasoning. And so this is the outline and objective of my talk. I kind of hope that I can persuade you that we should actually look more into video rather than images. And then in particular, look into the visual relation inference in addition to just object recognition. And in order to make your kind of AI model robust, I think we also need to look into causal reasoning. Yeah, and then I kind of quickly conclude the talk with a bit of future work and summary. Yeah. Okay, so so actually we are kind of talking about multimedia type of research. Yeah, and if you all were to recall, I think maybe most of you are not old enough. I guess the first multimedia conference actually started in 1993. I think since 1993 to about 2000, I think most of the kind of papers in the multimedia conferences are basically visual based. In fact, in ACM Multimedia 1997, we had a retreat. Actually, is basically to discuss how to define a multimedia paper that it should include not just visual, but should include more than one type of media. Yeah. So text was actually added in 2000 with the successful launch of the so-called track bit evaluation, and in particular on news video retrieval. Our experience in around 2000 is that with news video retrieval, with the clear anchor person speech, we can actually extract very high quality speech to text. And based on the text alone and a bit of kind of segmentation, visual segmentation, we are able to kind of do a very high quality news level retrieval. In fact, visual is probably secondary. And so actually for track bit, in order to make visual important, we basically focus a lot more at the short retrieval. In the sense that I want to know when is a person shaking hand with other person, when is a person entering the car, leaving a room, standing next to each other, and so on, right? So these are kind of very visual based. So in fact, let's set the stage that for visual, I think we typically look into very fine-grained kind of a recognition or semantics. And I guess in the middle of 2000, with the arrival kind of popularity of social media, I think this bring another boost to social media. I think for the first time, we got large-scale image data set with text annotation. And of course, the challenge here is that the text annotation are typically incomplete and also have some noise. And so this leads to a lot of kind of large-scale auto annotation methods and systems. I think from all the experience, we shows that actually visual processing alone is inadequate for a lot of applications. Although nowadays, I think we see a lot of kind of a visual-based type of application, but these are kind of limited to very kind of fine-grained type of retrieval. For example, in surveillance applications, face, body recognition. In e-commerce, maybe the fashion retrieval, the object recognition, and so on. Yeah. So actually, in a way, visual is a weak link if you want to apply kind of multimedia technology to a very generic applications. So in fact, this talk actually, I'm kind of focusing on how to improve the semantics of visual contents. So I guess we probably can clearly see we need actually fine-grained annotation in order to improve the visual contents, in addition to interpretability. And for the last 10 years, I think we've been working on object recognition with the launch of kind of ImageNet data set with 1,000 concepts in 1 million images. I think since the arrival of deep learning, I think the accuracy, so-called the error rate, has been dropping, as shown in this diagram. And watershed time is actually in 2015. For the first time, we show that based on this data set, machine actually perform much better than human. Yeah, but of course, I must qualify that this is only based on this data set. In general, actually, human is still a lot more robust than machine in recognizing all kinds of things. So the question is actually, is object recognition sufficient, right? So if, for example, if I look at this picture, right, there are two persons here, but is it enough to recognize there are two persons, there's a clock tower, there's a series of cars and things like that? I think of more interest or in terms of deeper semantics, I actually want to know what these two persons are doing. Are they talking to each other? Are they shaking hands? Are they standing next to each other? Is one person taller than the other person? Are they standing next to the road, and so on, right? So in fact, to achieve this, we need to actually do relation inference. In a way, we are looking into the so-called basic knowledge triggers of can we extract the subject predicate objects. Once we have a sufficient subject predicate object from this image, then we can actually do a lot of high-level tasks. For example, we are able to kind of figure out which are the dominant relations and then able to use it to describe this video, which is two persons talking next to the road under the clock tower. Or we can actually use it to answer BQA and so on. Yeah. So in fact, some early work actually was done in 2017. Actually, the work is probably more than 5-6 years ago. So most of the early work actually based on the so-called Trans-E framework, which is a framework to translate from feature domain to relation domain, and is very successfully applied to text. So in visual, I think the feature domain will be the kind of object, kind of feature representation of, or so-called embedding representation of object and subjects. And the relation domain will be another space. So the key problem here is, can we translate from visual domain of object and subject to the relation domain? So through the learning of these two matrices, right? And one of the early work done in 2017 is basically to look into visual translation embedding network, which is done in our group. And these are the kind of results we can get on the two data sets. One is on visual relation data set, and one is on genome data set with the accuracy of about 7% to 14% respectively, right? So I guess on most of the easy cases, you can see the green one is accurate retrieval, the red one is wrong retrieval. So you can see the retrieval, I mean, I show you only the good one, so it looks pretty good. I guess the question next will be, is image the right domain to do visual kind of relation? Yeah, but I guess we can observe that actually a lot of relations are transient. So for example, if there's a dog standing on the surfboard, is the dog riding the surfboard or the dog just standing there? Somebody catching the ball, is it catching the ball or throwing the ball? I think I guess if you do very detailed analysis, you might be able to tell the difference. And is this person getting on, getting off? Is somebody entering the house or leaving the house, and so on, right? So in fact, there's a lot of features that actually you require video to actually make a difference. So in fact, I'm advocating that actually to do a good visual relation type of the work, actually you need to look at video. Yeah, there are 3 challenges, I guess. I think the first is that the visual relation tend to be very highly variance, very diverse. But again, this applies to image as well. So for the same subject and object, a person and a dog, there could be multiple relations. A person can be feeding the dog, can be touching the dog, can be washing the dog, and so on. But for the same kind of a relation, actually you can have multiple subject and object. So for example, a person can ride elephant, person can ride bicycle, a bear can ride bicycle, and things like that, right? So it's kind of quite varied. The second, which is kind of more related to visual, is that actually there are lots of transient visual relation that can only be detected in video. For example, is the dog walking faster than the man? Is the dog walking beside the man, walking with the man, and so on, right? So this is require kind of video to actually do this kind of analysis. And the third one, of course, if you can see from here, of course, this is simple video that the relationship changes, right? So the dog was behind the man, then the dog walked with the man, then the dog later on walked in front of the man, right? And if you can, there are lots of kind of more complicated video where the changes in relationship is actually a lot more complex. So the relationship in video, in the short video, is actually dynamics. And we need to take this into considerations. Okay, yeah. So yeah, I'm just looking at the chat to see anything related to my talk. Yeah. Okay. So in order to promote this task, actually we kind of annotate a data set. You can see from this data set here that we have do very fine-grained annotation of subject of kind of relationship between 2 subjects and so on. And as you can see, this actually form the basis for many downstream video processing tasks. Okay, sorry, too fast. Yeah. So the data set consists of 10,000 videos actually selected from YFCC, which is kind of I can't remember, from the Yahoo kind of image data set, with 35 object classes and 132 predicates. And this is a very complex crowdsourcing project. Actually, it took us more than a year just to tag this data set. And I guess we will not want to do it again. Yeah. Okay, so given a video, actually, I think the first task is basically to kind of figure out where is the kind of object tracked of a person. So for example, the lady, we're going to track her over all the frames so that we can form a kind of a track, or you call it kind of spatial temporal grounding. With the spatial temporal grounding of all the objects or subject, whatever, we can then actually form the so-called knowledge graph. Scene graph. And or we call it scene relation graph. The key difference in video is that this, as I mentioned, the relation will change. So in fact, this scene graph is actually dynamic. So actually how to represent and generate a dynamic scene graph is actually a big challenge. And in fact, this is the ultimate goal of video semantics. I guess if I can extract this out, then I can figure out all the semantics of the video. Yeah. And so we also need to do high order relation recognition. In fact, the most importantly, a very simple task, which is kind of not of interest to most people, actually will play a big role. For example, accurate tracking of long-term object tracks. In fact, this is a very hard task, but I feel that it's kind of under not of primary interest right now, but it is very important. Okay, so one of the tasks is basically video relation grounding, right? Given the subject, object, and the predicate. So, for example, a person jumped about a bicycle. We want to figure out which part of video contains this, and more importantly, we also want to identify what is the position of object and subject in green and red in this example, right? So the output should be, given a video segment, I want to output the part of the segments in the video with the kind of a detailed location annotation of subject and object to indicate where this relation triplets happens. Yeah. So one work that we have done is basically to kind of make use of video relation grounding network, and by looking into hierarchical encoding, and this helps us to basically identify this to reasonable level accuracy. Yeah. So I will not get into detail, but kind of show you the results that. Yeah. So this is kind of one of the examples that we are able to kind of single out a man riding a bike within this particular video, and of course the other examples would be a man feeding elephant, a man ride bicycle, and so on. Yeah. Most of the current framework actually based on component-based video relation framework. I think this framework consists of 3 components. The first is basically object tracker proposal. So given a video, we want to figure out where the object tracks. But of course, to do it at the whole video level is very difficult. So typically we do it at the segment level. In this example, the segment is 30 frames with an overlap of 15 frames. And then for each segment, we want to figure out where the track of that objects. Yeah. And of course, the video grounding method actually we discussed previously can be used for this task. Second, given all the tracklets, the next task is basically to do relation prediction, right? So given the subject and object tracks, we typically extract features like the class me feature, basically the vector of all the possible classes, the dense trajectory features, and also the relative position between the 2 objects, subject and object, and then use that to basically predict under the kind of unified training loss to predict the possible predicates. Okay, so once we have the subject, object, and the possible list of predicates, then the next thing is basically to kind of but these are all done at the segment level, which is kind of the difference in this case, and then we need to chain them up so that we can find the beginning and end of the presence of these visual relations within the video. Yeah. So basically, we kind of utilize information from the whole long-term relation hypothesis, and then to maintain multiple possibilities, and then make the decision at the very last minute, with so-called kind of a multiple hypothesis association. Yeah. So these are the kind of early results in around. I guess this latest paper was in 2020. Yeah, so it's kind of the early results in 2020. The accuracy is still pretty low. Yeah, in fact, that shows you that there are lots of rooms for this line of research. And there's a lot of other work on end-to-end, but kind of end-to-end performance is kind of similar, because this is a very complex task to be done end-to-end. And so the next I want to introduce we basically use this data set as a basis for ACM Grand Challenge. So we have been organizing this task since 2018. So this is probably the fourth year that we're organizing it. And this year is actually led by Dr. Chua, which is a postdoc in my group. And so the basic task will be, as I explained before, given a video, I want the system to be able to find all non-trivial relation triplets. That means a list of non-trivial subject, object, and predicate, as well as accurately determine their positions and the beginning and the end. Yeah. So this is kind of quite a important, difficult task. And for this year, we have 48 groups participating, kind of more than last year, which is 41, and then 11 groups eventually submitted the results, up from 8 last year. Just want to show you, these are the top 3 groups. In fact, the top 2 groups actually performed better than the second best of last year. We did not include the best of last year because the best of last year, they added a lot of kind of external data and things like that. So it's not kind of a fair comparison. So based on the standard setting, the current MAP is about 0.0948, which is actually a vast improvement over the last years. And if we look at the reason for the improvement, as I mentioned earlier, in fact, is something that is not very sexy at the moment, which is basically you do a better tractor-based visual tracking and the transformers. Yeah. If we look at kind of the visual relation task, there are actually four steps, right? And these are the kind of popular techniques. And the red color, just to show you that these are the techniques actually work extremely well for visual relation. So at the frame level, object detection level, the cascade RCNN, which is kind of a multi-stage object classification framework at the object level, actually performs the best. At the object tracking level, the use of sequence non-maximum suppression method actually works the best. And the feature, of course, with positional feature is important. And of course, the multi-hypothesis method actually works the best. Okay, so far, I think I kind of gone through the basic methods, which is kind of based on the detection of subject and object. When given subject and object, then we predict the predicate. So you can think of it as a cascade-based method. Right? And in fact, this is one pass method. We detect all the subject and object, and then use it to predict the predicates. So the question is, can we do better? Of course, the intuition quickly is that maybe we can make use of domain knowledge. Say, given a subject and object in the context, say, for example, 2 persons sitting on a table opposite each other, what are the possible relation can that be? I guess they're probably discussing, eating, or working together or something like that. Yeah. And then secondly is, can we actually come with methods to basically extract kind of visual knowledge from those pre-trained models? So for example, the current prompt-based method and so on. So I just quickly go through these 2 works that represent some of our recent works. So to leverage domain or common sense knowledge, I think we can always make use of knowledge graph or large-scale kind of language model and things like that to basically compute all the probability of given a predicate, given a subject object, given two members of this predicate, what is the likely occurrence of the third one? Yeah. So in fact, this is what we have done. Yeah. So given the subject and object, we want to make use of knowledge and common sense knowledge to predict what could be the predicate. Right. So in a way, it's given subject, object, and then we want to basically predict the predicate. And then we can do the same thing for the subject given the predicate and object, or object given the predicate and subject, and so on. Right. And in a way, this process can be iterated until convergence. And of course, right now there's no proof of this conversion, but empirically we can show that actually you converge within 2 or 3 iterations. And so this is basically an iterative approach by using the recognition of subject and object to predict predicate and so on, and then given the latest subject and object to give a better prediction of predicate and so on. And the same for object and subject. Yeah. And this actually leads to substantial improvement. And of course, the future work can be achieved by incorporating the kind of pre-trained models into the learning process. And this paper was actually just presented last week, actually, in the ACM Multimedia Conference. Yeah. I guess another area is basically, can we use the prompt-based method and things like that to basically help the system to do the prediction better? I guess prompt in natural language is that I'm giving you a prompt to help you to give me the right answer, right? So sometimes I ask you a question, then I give you different hints and things like that. And these hints will help you to come up with a good answer. And this is probably currently one of the hottest topic in NLP now, which is kind of prompt-based method to elicit knowledge from the pre-trained model. So for example, given the text, I love this movie, and I want to know if the sentiment of this sentence, is this positive or negative? So I can come with a prompt, say X, which is I love this movie. Then the prompt was, overall, it was a Z movie, where Z is a mask component. So you want a system to basically predict what should be in Z. Is it a positive or negative? Right, or different factors. Yeah. So basically you convert it into a kind of mask task. And this is actually very powerful, and hence this is actually very popular. Yeah. So I guess so this one task that we do basically is kind of to convert, given a lady looking at horses. So I guess the question would be sorry, what's the horses washed by the woman, right? So I suppose, so basically one work that we've done actually is that we represent the feature as a kind of color blocks to simplify the process. And then so given this prompt, we hope the system able to say the lady is looking at the red block or the blue block, and kind of this simplify the whole prediction process. And again, this we can show that this leads to a substantial improvement. And this work is actually submitted to one of the conferences recently. And further research, of course, is that we want to basically look at prompt-based approach to distill visual and multimedia knowledge. Yeah. Okay, so beyond that, I guess the finding is that actually to do well on visual relation, actually we need actually a lot of kind of very good basic visual techniques. As I mentioned before, representational model, tractor detection, which is overlook, and also the video grounding models. We also need to, yes, the ultimate goal of visual detection is to come up with a dynamic scene graph. So we need to be able to model the dynamic context, interaction, and relation well. And these are actually a difficult research problem. And of course, able to identify dominant and eliminate trivial relations. And finally, of course, in all learning methods, the kind of out of distribution problem is always a concern, right? And this applies to visual relation because most of the triplets actually are zero-shot cases. Yeah, because the combination of subject, object, predicate is so high that there's no way that you can see most of them in the training samples, right? So the OOD is basically a kind of basic problem in this sort of method, and so we need to address the OOD problem. And of course, one approach I want to look at is the causal reasoning. Yeah, so I'm just looking at the time, so maybe I need to rush a little bit. Yeah, so causal reasoning, actually, I'm kind of based on the 3-layer causal reasoning hierarchy that is kind of proposed by Julia Kerr in the Book of Why. So causal reasoning, we say we want to basically, it's a process of identifying causality relation between a cause and its effect. And the first layer is that given the data is so-called seeing, right? In fact, this is kind of a correlation. We want to see what is the obvious relationship between different components in the data. Second level is basically intervention. Can we change some of the data value and things like that, and then to evaluate its impact? And the third layer is counterfacturing. Basically, can we imagine that things are happening in different way? So for example, this is used in financial modeling. Say, if I were to give everybody $1,000, how would it impact the economy? Yeah, if I reduce the tax by 1%, how would it impact the economy and so on? So these are basically all the counterfacturing examples, and this has been used to address OOD and bias problems. Yeah. So just to give a quick examples, I think this probably you've seen this example before. So there's a kind of a chart on the chocolate consumption on the x-axis and the number of Nobel Prize per million population in the y-axis. And then you can see actually most of the Western countries are all high up here. And the top, of course, is Switzerland. And the two Eastern countries here will be Japan and China, which is at the bottom, right? So you can, by observing the data, so basically kind of association, you can see that there's a strong correlation between chocolate consumption and Nobel Prize. So I suppose if you take this as a result, then you would say maybe I'll encourage everybody to eat more chocolate, then our country will have more Nobel Prize winner. And of course, intervention, well, of course, we know that this is spurious correlation. And intervention is say, yeah, if the Japanese or Chinese eat more chocolate, will they get more Nobel Prize? And the third is counterfacturing, is to imagine that if the Swiss doesn't eat that much chocolate, would they drop from the league to the bottom and so on? Yeah. So of course, we know chocolate is not a cause; it's just a spurious correlation, right? So in fact, how to identify and overcome spurious correlation is key to causal reasoning, right? So of course we know the reason of causing this spurious correlation is the chocolate, and chocolate is a confounder. Chocolate actually causes all the statistics to be correlated, and so first of all we need to identify the confounder. The other example would be, supposing I have a publisher located in city X publish fake news, and then a naive classifier would basically classify that this city is related to fake news. So we know the confounder is a city, right? Kind of back to kind of visual example, if all the images of dogs are in green background, then a naive classifier will basically use a green background to associate with dogs. So now given a dog in the snow background, the classifier will probably fail, right? So basically the confounder here, in both cases, are the location. The key question is how can we remove that confounders, right? So the so-called causal reasoning is basically can we remove the confounder by blocking the influence of the confounder? And then so in a way you need to perform the so-called second level of causal hierarchy. That means to perform intervention by blocking the influence of the confounder, so that the true causal effect can be propagated. So the solution approach is basically to identify the confounders, generate the causal graph, and then perform the causal intervention. Yeah. So I think basically this is a basic approach. I'll give you 4 examples, and then I'll go through quickly in these 4 examples. I think one of the early work was done in 2010 by Han Won Kang, actually for NTU, which was previously from my group. So it's basically on Seng graph. So the observation is that the Seng graph, we tend to actually identify the relationship between, for example, the motorbike and the man. We tend to actually identify a very common relationship instead of the more detailed relationship. There's a man behind the motorbike. This man actually, and so on. Because the near is actually happen most of the time. So in fact, the system will basically predict that to be the case. So how to overcome? So this is basically the kind of long-tail bias. Yeah, and so we can come with a causal graph here. This is the prediction, the predicate we want to predict. Say in this case, riding, and this is the object features of man and the horse, and these are the whole image, including the background, and that's a label. So we know that basically, given the label, without doing too much of detailed analysis, we tend to basically rely on the learned attributes, learned learn correlation, which is kind of contain a lot of bias, and this tend to give you the result as the most popular kind of head tail kind of results, right? So one approach to be taken is that given these two objects, if we just do the learn statistics, it will predict that on is the most popular, so you tend to predict on without looking at the visual feature. So the intervention is that we want to force the system to look more into the visual feature, right? So one way is that we can compare the results of the full image, background, subject, and object, as well with the image where the subject object removed. We're just using the background to do the prediction. If we do the subtraction of A to B, that means we are actually remove the influence of the background, and then to elevate the influence of the subject and object. Okay, so that's the whole idea. Yeah. So you can look at this Cursor graph by removing this part to kind of cause the system to basically do the retrieval, do the prediction based on background, and then do the subtraction to kind of to bring out the influence of the subject and object. And you can see there's a vast improvements in the results. Yeah. And I guess another example would be kind of elephant with the man. Yeah. And whether this is right or fit. And of course, most of the time it's fit. So the state-of-art method can predict is a right. Yeah. The reason, of course, is again the long tail prediction type of problem. So the causal intervention again is that we want to come up with a causal intervention by forcing the system to look at all possible predicates instead of just based on the learned correlations. Yeah. So by doing the do calculus, by forcing the model to evaluate all the possible predicates, then we are able to kind of identify which are the true predicates that are likely to happen, but not influenced by the head kind of popular relations. The other example will be kind of based on the so-called video moment retrieval. So given a query, we want to know exactly which part of the video that it happens. And we know that there's a lot of biases because it depends on the verb in the query. Supposing if it's open, it tends to happen at the beginning of the video. If it's end, it happens at the end of the video, and so on, right? So I suppose the problem is that can we remove the confounder relation between this and the video, and so we go through this disentangling process, and then the intervention is that this force the system to evaluate all the locations, and that gives us a much more accurate results. Okay, I think yeah, I again for recommendation we can look at that the kind of click bias, because item 2 actually the feature you look at and the actual content is different, so that's why you get inconsistent user evaluations, right? So the whole idea will be that we can actually overcome that by post-click feature, but of course we don't have. So the whole idea is that can we do the overall evaluation, and then one evaluation with the pre-click feature, and the subtraction will give you the effect without the pre-click feature, which help us to remove the influence of the pre-click feature. Yeah. Okay, so I think I kind of quickly summarize this part. Basically, we are looking at causal influence by identifying the confounder, and then put in the using the intervention to remove the impact of the confounders. The next level, of course, is counterfactual reasoning. Yeah, we want to basically kind of instead of just one pass, we want to basically identify if this is different, if that is different, what would be the evaluation. So currently, the work that we're doing is basically, can we do counter double checking? If the result is not clear, can we double check if this is different? What would the impact would it be? So this is kind of a counterfactual reasoning. And most of the research right now is basically given the set of data, we come out with a causal graph. and then use the causal graph to do the intervention to come up with the outcome, right? So causal graph is done manually, yeah. And one key research is basically causal discovery. Given the data, can we figure out which part of the data are conditionally dependent so that we can remove that condition as a confounder automatically, so we can actually do this whole process of causal inference and causal discovery automatically. Okay, so now I'll quickly summarize. I think just to say that the visual detection actually is just an early part of the task. In fact, once I can do the relation, actually I can use it to do other tasks. For example, the higher level tasks to say that, oh, this is a happy family. I can even predict that the mother might hug the baby and things like that. And of course, there are other tasks like video description, video QA, future activity prediction, and so on. This cannot be done with the help of visual relations. And that helps to basically, other research will be transfer learning, future learning, because the tagging of this visual relation is actually a very, very difficult task. Yeah. And for specifically for visual relation inference, I think we have done some work in 2020 to basically evaluate the difficult QA question of why and temporal. And we found that actually most of the current state-of-the-art methods don't do very well at these two tasks. And I guess I just want to point out that to improve on the visual relation inference, actually we need to actually capture the relation between subject and object much better. Okay, so finally, I think that's my last slide. So we are in a very exciting era. I think we should actually looking at visual relation so that to bring the semantics of the visual to that of text. And this is very challenging because the accuracy of visual relation right now is actually very low. And of course, there are various methods to improve on it. And the observation that most of the visual relations are actually a zero-shot learning task. And so the training and testing tend to be OOD type of problem. So to improve OOD and robustness, we need kind of a causal reasoning to be one important method to do that. So research of both are actually emerging and challenging, and they opens up a lot of avenues for new research. And so it's a great opportunity for deep research with broad applications. Okay, so I just acknowledge the help of my groups and my postdoc, my students, and some visiting students and so on. Yeah. Okay. So sorry, I'm kind of a bit overrun, but anyway.
Thank you, Professor Chua. I would like to now introduce Dr. Saritpati Goswami from Huawei Technologies, who will be handling the Q&A for this session. Over to you, Dr. Sarit.
Thank you, Anvit. Thank you, Professor Chua. So we have a lot of questions actually that have been posted. So I'll start with first few. So first question is, how do you actually so the first question is, how far are we from detecting symbolism of a given visual?
Sorry, the what?
Yes. So how far are we from detecting a concept or an idea from a given video?
I guess what I'm trying to say is actually at the object detection level, we are doing very well now. Of course, on the data set, we claim that we do better than human, but of course, humans are a lot more robust. So object recognition, I would say in most of the domain is kind of, I wouldn't say a soft problem, but the solution is good enough for a lot of applications. For example, face recognition, product recognition, clothing recognition. These are actually very mature now. The difficult part is actually relation inference. Basically, kind of to the key elements of that basic kind of knowledge triplets. The accuracy right now is very low. I think you can see from the result, it's not even 10% yet. It's all less than 10%. And so I guess the kind of problem is that the relation is usually very fine-grained. So we need to figure out how to make use of large-scale pre-trained, large-scale data set to kind of using distance supervision or other unsupervised method to basically learn the relations. I think this is a big challenging problem. Yeah.
And in that case, if there are changes in shot or scenes, with the subject remaining constant, but the scene changes, can it still be detected and some relationship inferred?
Yeah, I guess this one you got to fall back to the basic. I mean, right from, I mean, in 30, 40 years ago, the first task of video task is basically to do shot segmentation, right? So we assume that a different shot will have a different scene with a slightly different semantics. And so basically we should be looking at detecting all this at the shot level. I think once you're at the shot level, then we can actually combine the shot into the higher level. But if we kind of looking at the shot level is coherence, then I think the thing that you mentioned will not be happening. But of course, even coherence, the relation would be different as well. So in fact, that's a challenging task.
Another question: has visual relation inference technology come to a stage where it can be used for commercial applications? If no, where do you see it reaching at that accuracy level?
I guess I see the visual relation at the, I mean, there's a lot of tasks at the image level now, because I think at the image, we got lots of annotation data, basically, and make use of the combination of text and visual, we can achieve reasonable accuracy. So I guess the first will be happening in specific domain, for example, in product, fashion search, and so on, because the type of relations are quite limited. And so given a huge amount of data with some annotation, with a bit of visual, plus a lot of kind of distance supervision based on NLP, we can actually do a very good job. I think that's what I see will happen now. And the next level, of course, is if we go to visual, we need to select certain domain whereby visual relation can be done well, and then we can use that to basically demonstrate the video QA, and that's probably the direction that most people are working on.
Okay, thank you very much, Professor Chua.
Yeah.
Over to you, Anvit.
Thank you so much, Professor Chua, for that lovely session. And thanks to all the audience for asking your questions as well. If you have any more questions, please use the Q&A. Once again, I'd like to thank Professor Seng Chua from the NUS-Tsinghua Next. Thank you for sparing your time and for that lovely session, sir.
Yeah, thank you very much. Yeah, and too bad I cannot give this presentation face-to-face, but of course, hope in the near future we can do it.
Absolutely, sir. We definitely hope that we can have an in-person session very soon.